Yeah, I appreciate the opportunity to talk here and share the stage with the legends of neuromorphic computing. I'm going to be talking about something a little bit out there, maybe. So my name is Jeff Shainline. I work at NIST Boulder. With this team of folks, I'll be showing experimental results acquired by a lot of those people. And I started this physics and hardware for information project a few years ago with one maiden question on my mind, which is if we try to achieve artificial general intelligence, what kind of physical limitations are we going to run into? And I don't claim to have answered that question, but in this neuron design right here, you'll see some of the things I'm thinking through to try and anticipate what problems we might run into, what physical limitations we might run into, and how to overcome them. So let me break down my title so you can understand what I'm talking about here. First of all, I say synapse events. So clearly I'm talking about, well, I say synapse, so neural networks, but also events. So I am talking about spiking neural networks. It's not obvious that spiking neural networks are the best path to general intelligence, but that's a conjecture that I make. I say photonic synapse events because I am interested in using light for communication. So I'll talk a fair amount about that. And then fluxonic processing, which most people in this audience are probably not familiar with. Fluxons are generated by Josephson junctions in superconducting electronic circuits. You don't need to know very much about that for this talk, and I will explain what's needed. But there's actually two ways that we're using superconducting electronics here. One is for photon detection. By using superconducting single photon detectors, we can detect the smallest possible amount of light, 1 photon. But also, in addition to communication, we're using it for all of the neural computation that happens here. So in this entire system, communication is done with light, and it's always binary, and all the information processing happens in the electronic domain. That includes memory. So you're not going to go to all the trouble of making superconductors and optoelectronic circuits if you're going to try and put it in your cell phone. That's obviously not where we're going. This is neuromorphic supercomputing. Our goal is the highest performing neuromorphic system that is physically achievable. Whether or not we are on the right path, that's open for debate. OK, so let me start by answering the question, why are we using light for communication? There's actually a lot that goes into this, so I'm just going to kind of gloss over it. But one specific example, say you take an arbitrary network. You can calculate the path length, the shortest average path length, where you calculate the distance from each node to every other node and average over the nodes in the network. So take this plot. Consider a random network where you have a sort of lower bound on the average path length for a given number of nodes connected by a given number of edges. What this plot is showing is for a network with a given total number of nodes, what average degree of your nodes do you need in order to maintain a certain path length? So if you take the average path length of 2, which is the target, you don't want an average path length of 1, which would mean every node is connected to every other node. That's overkill. But you don't want to let it drop to 3 because performance drops significantly. So take a specific example. You have a network with 1 million nodes. You find that you need, on average, about 1,000 connections per node in order to maintain that average path length of about 2. Or an extreme example, you have 100 million nodes in your network. You need about 10,000 connections per node for a short average path length. This is very similar to the hippocampus in the brain, where you have about 100 million nodes, and they each have about 10,000 connections. This is one of the reasons why. So I'm talking about why we need light for communication, and I'm arguing that information integration, efficiently exchanging information across the network, requires a short path length, and that requires very high degree nodes, 10,000 node connections per node. Maybe this isn't news to this audience. There are different ways to achieve this, address event representation, other things. But this is central to our decision to use light for communication. We want to be able to efficiently integrate information across space, and we don't want to have to deal with charge-based parasitics like capacitance and resistance. So that's why we choose light for communication. But light sources are a challenge. I think if we could make light sources that were as simple as a transistor, we would not be having this discussion. There would be optical communication in every single one of our devices. But we can't make light sources that are as simple as transistors at room temperature. Usually it requires 3-5 integration, and that's complex. And that's why this is not a no-brainer. So OK, I'll come back to the question of light sources. But first, I want to discuss how we implement the passive aspect of photonic neural networks. Suppose we already have light sources. How do you route the light from each neuron to its 10,000 connections? Well, you have to use multiple planes of waveguides, just like you have to use multiple planes of wires in an electronics process. So we've developed this multiplanar photonics process at NIST. We're doing it with amorphous silicon as well as silicon nitride. The core device is this tap and transition device. If light is coming through this main bus waveguide, you tap off a desired fraction, route it up to the upper plane, and then go the other way so you can make these efficient crossovers. This is our best experimental data on this to date, where you have basically a 10 to 10 feed-forward neural network with all-to-all connectivity. So you can think of each of these as a neuron and each of these as a synapse. Each neuron is going to route light to each of its downstream connections. So here it is in operation, an optical fibers coming in, coupling light into the matrix here. And you see each of the outputs, one synapse at each output neuron is lit up. They're not all uniform. We've intentionally routed it with a Gaussian profile just to show that we can. In general, we want one photon to arrive at each of our synaptic connections, but we also want to demonstrate that we can get the light wherever we want. So that was the motivation here. And we want to scale this to 3D. We're targeting something like 10 planes eventually. OK, so that's a crash course in why we're using light for communication, but I haven't said really too much about why superconductors. So let's talk about the first part of that, the detectors. Here's a superconducting nanowire single photon detector, which I'll refer to as an SPD in this talk. When this detector is in the superconducting state, this is a resistanceless path to ground, so current flows straight from the source to ground. When a photon comes in, it disrupts superconductivity, causing a small resistive section, and that diverts the current that was flowing through this nanowire across some load, our SPD here. That's your photon detection event. It looks like this in the time domain. I'm plotting the current flowing through this resistor after a photon is detected. You pop that current up, and then it returns to the superconducting path with the L/R time constant that you engineer into the circuit. This is the single photon detector. Inductor in series with a variable resistor. The variable resistor goes from 0 resistance to a very high resistance like a kiloohm in under a nanosecond. So we've made these single photon detectors. Most of you probably aren't familiar with the group I work in with Seiwu Nam, but he's pioneered a lot of this work. What I've been able to contribute is the ability to bring these into the integrated photonic context. So here we have a photonic circuit with a waveguide going through, ring resonator dropping light to a superconducting detector. Here's a scanning electron microscope zoom in. The little purple wire is the single photon detector. It's just a wire. It's that easy to make. So it's very scalable. It contributes to efficiency in two ways. First, the lowest possible light level. Once you've decided to send optical signals between your neurons, you can't do better than one photon per synaptic communication event. But also, because it's superconducting, it doesn't draw power in the steady state. When current is flowing through it without detecting photons, it's not dissipating any power, which is crucial in the sparse coding regime that neuromorphic circuits operate. So here's some data from that circuit. Light comes in through an optical fiber to this waveguide. On resonance with each of these rings, it drops the light to each of these superconducting detectors. So what we're plotting here is the counts per second coming out of each of these detectors as a function of the wavelength. And you can see that we've imprinted the frequency response of the photonic circuit on the electronic component. This is, again, not necessary for neuromorphic computing. It's just an example to show that we can control these various devices. And we truly have waveguide integration. The light's not getting to the detector through some other scattering pathway. The downside, superconductors don't work above 4 Kelvin. So everything I'm going to say requires operating at 4 Kelvin. And so some of you might leave the room, but I'll try and convince you by the end that that's not as bad as it seems. Because the upside of the downside is that when you're operating at 4 Kelvin, now you have silicon light sources. If, like I said, you had light sources that were as simple as transistors, we would not be having this conversation. I contend that we do have light sources that are as simple as transistors. So here I'm showing an all-silicon light-emitting diode. This is clearly a cartoon. The idea is you have a PIN junction. You've implanted some silicon ions into the intrinsic region, and then you anneal it at about 250 C to produce optically active point defects called W centers. And then when you forward bias this, they recombine through dipole emission, and you get light out coupled to your waveguide. Here's data showing it works. We have an LED right here coupled through a waveguide to a nanowire. And this plot is showing the counts per second on this nanowire as a function of the LED forward bias current. And you can see that we have established an optical link with about 1 million photons per second getting from the source to the detector. And on this detector over here, which is not connected to the LED by a waveguide, we're down by about 40 dB. So the light is truly coupled in through the waveguide. So these light sources, I actually think they're simpler than transistors. It's about a micron feature size and dead easy to make, just 3 implants. Okay, so I talked about light, I talked about detectors, and I talked about the light sources. Now I want to talk about how the superconducting electronics works, because this is what makes this not just good for communication, but a neuromorphic platform that's actually good at neuromorphic computing. And it all comes down to Josephson junctions. So the way it works, I discussed how this single photon detector works. Basically now all I'm doing is adding a Josephson junction in parallel with the single photon detector. So if you don't know anything else about a Josephson junction, you need to know 2 things. One is that a Josephson junction has a critical current. When it's below its critical current, it's a superconducting path to ground. When the critical current is exceeded, a voltage develops across the JSF. I'm calling this the synaptic firing junction. And so the first thing you need to know is it has a critical current. The second thing you need to know is that when you exceed the critical current, it develops a voltage, but the voltage comes in pulses that look like this. And these are fluxons, okay? So I'm holding this junction above critical current. It's popping off a fluxon with a given rate, and the rate depends on how far above the critical current you are. So the current of each of these fluxons is going to be quantized. This is the magnetic flux quantum, an immutable constant of nature. And the inductance is a circuit parameter that we get to set. So we can change how much current is generated for each fluxon that we generate. And we do that by changing this inductance here, but we can also change how many fluxons are generated when a synaptic firing event occurs through this current bias, the synaptic bias current that I'll talk about more. So the basic idea, photon comes in, that diverts the current out of the single photon detector across the Josephson junction, and that produces an amount of current that we can change with a synaptic bias current, and I'll describe how that works. The number of fluxons is some function of this current. Okay, so I'm skipping a couple steps here, but this is the entire synapse. You have this receiver portion right here that takes in a photon and converts it to the electrical domain. And then you have an integration portion right here where you have the postsynaptic current. That postsynaptic current is the fluxons that propagated across this simple transmission line and are now stored in an LR loop. So the current that you just generated is going to stay there for the LSI over RSI time constant. This is just like a membrane membrane time constant in a neuron, except we can choose these values over 10 orders of magnitude or something. So we can have very fast relaxation or very long-term memory retention of synaptic events. This is not going to operate in isolation. It's going to eventually be coupled either to a neuron or a dendrite. So I'm labeling this the dendritic receiving loop, which I will talk about more in just a second. Okay, so here's my neuron picture from the beginning. I've now talked about the synapses. Some of them are excitatory. They're also inhibitory. They're going to go into dendrites, which perform intermediate nonlinear computations on the signals. And then eventually, they will connect to a neuron, which will perform the final thresholding step, produce an electrical signal that will generate light out of one of those silicon LEDs that I just talked about, and that light will go to downstream connections, 10,000 of them, something on that order, and that's how these neurons are going to work. So this block that I just described is one of these synapses here. Photon in, electrical signal out, all the computations in the electrical domain. Okay, I said I would tell you how the synaptic weight affects the amount of current generated. That is this plot right here. I'm plotting the number of fluxons generated as a function of the synaptic bias current. Now, you can translate from the number of fluxons to the total net amount of current by the inductance there, but that's not a very important point. The important point is that this is a slowly varying function. There are 3 things that make this actually a good way to set a synaptic weight. One is that it's slowly varying. So small changes in your synaptic bias current result in small changes in your synaptic efficacy. It's also monotonic, so if you keep increasing this knob, you never go over a hump and then come back down again. And it's also, you can engineer your circuit so this is bounded, meaning that there's a set minimum synaptic weight and a set maximum synaptic weight. So if you have some either supervised or unsupervised training algorithm, it's not going to run away without bound. You're going to keep your synapses in a functional range. I want to talk about synaptic plasticity. So on first glance, I'm sure everybody thinks this circuit looks simple to understand. Okay, so the point here is this plot is probably more familiar to a lot of people. This is the usual spike timing dependent plasticity plot, where what I'm showing here is on the y-axis the change in the synaptic efficacy, and on the x-axis the difference in time between the arrival of a photon from the presynaptic neuron and the postsynaptic neuron. You see that if they're arriving in the constructive order, you increase the synaptic weight. And if they're arriving in the opposite anti-Hebbian order, you can decrease the synaptic weight. Those happen with this upper portion of the circuit here is a Hebbian block, and the lower portion is an anti-Hebbian. And the output of this circuit is that synaptic bias current that I've been talking about. So this is a block to show that we can do spike timing dependent plasticity with one photon for each step of the update operation. And also, if you notice, if you change this synaptic bias current here, you change the amount that the synaptic weight changes. So you're doing STDP, but you can change how much the synaptic weight changes with each update operation. So this is sort of a metaplasticity knob right here. So relatively elaborate neural mechanisms can be achieved in these circuits without a lot of effort. Okay, now I'm realizing just how many circuits there are up on the screen. This is the synapse that I talked about before, and everybody understands it now. So if you just quickly look over here, it's actually pretty much the same thing. I'm talking about a dendrite now, but it's doing the same thing. You have a receiver that takes in inputs from all your different synapses, maybe 1, maybe 10 of them. And when the current from all of those gets mutually inductively coupled into this loop and exceeds the dendritic firing junction critical current, then you pop a bunch of current into this loop, the dendritic integration loop. So it's really pretty much the same thing as a synapse, except two things. One, it's taking electrical inputs, not optical inputs. And two, you can put many different synapses on one dendrite, including inhibitory synapses, which is important, so you can functionally remove various different parts of the network dynamically as needed. So why do we care about dendritic processing? I actually think it's one of the most important things that neurons are doing. They perform intermediate nonlinearities between synapses and the soma. They perform temporal filtering on spike trains. They perform logical operations. So there's a lot of exciting things that we can do with this dendritic circuit. I'm only going to talk about a couple of them. And I just want to reiterate, now this block that I'm talking about is just this yellow cartoon block here. So there's always a one-to-one mapping between a block on here or a different component and the circuit that it actually refers to. So let's just start with the two. If you just have one synapse on one dendrite, that's when you're performing basically short-term synaptic plasticity. Facilitating or depressing are both possible. But I'm jumping ahead to two synapses, and now we're going to be performing basically coincidence detection. So if you have two different synapses coupled to the same dendrite, now what I'm plotting is the amount of current added to the dendritic integration loop, that's the post-dendritic current, as a function of the delay between the two synapse events. And you see it has, in this case, an exponential decay because we've outfitted each of these with 1 L/R time constant, which I'll remind you can be set in hardware across a very large range of values. And importantly, we can tune the response to this with the dendritic bias current, which is a lot like the synaptic bias current. It provides us a dynamic means to reconfigure our circuits and allows us to have access to various different learning mechanisms now at the dendritic level rather than the synaptic level. So these are logical operations. Basically, what you're performing is an AND in this case when the bias current is low, or an OR in the case where the bias current is high. Let's say we jump ahead now. Instead of 2, we have 10 synapses on one dendrite. Now I'm plotting the current added to the dendritic integration loop as a function of the number of synapses firing when they're all connected here. In this case, I'm assuming they're all firing coincidentally, and what you see is you have this highly nonlinear activation function, sort of sigmoidal looking. The point being, we have achieved an intermediate nonlinearity between the synapses and the cell body. The dendrite is performing a computation on its inputs. Okay, so this is the neuron as a whole. And we like to talk about superconducting optoelectronic networks, which are networks of these kinds of neurons. We call these loop neurons because there are all these integration loops. So we're talking about light for communication and superconductors for computation. And that's hard to make. That's not a standard process that exists anywhere in the world. So we've demonstrated a lot of the different parts at NIST. I showed you some of our data. But now we're seeking this full system level integration, your light sources, your Josephson junctions, your passive waveguides. So we're very excited to be working with SUNY Poly to develop this process at the 300 millimeter scale. So far, we have demonstrated these light sources on 300 millimeter wafers. So here's photoluminescence of those point defects I talked about, fabricated here at SUNY Poly by Papa Rao and his team, and measured at NIST by our team. So we have the light sources at the 300 millimeter scale. We need to make them electrically integrated, integrate them with superconducting detectors and other things, but this is encouraging to see. So now I probably am out of time. What do I have?
A few minutes.
Okay, so I'm just going to sketch out a vision of why would you go to all the trouble to combine light and superconductors? Most of your answer is probably, I'm not going to do that. But suppose one was going to do that. Let's just step through this vision here. Okay, so starting with wafer scale modules. Now we're talking about a 300 millimeter wafer. You'll see in a second why I've cut it into an octagon. But you see you have a dense network of on-chip waveguides. Your neurons are on here. You can fit about 1 to 10 million neurons on a wafer, which is big. I understand these are big neurons, but we're not done there. So we can use free space coupling to communicate between planes of stacked wafers, much like a column in the brain. I'm referencing Mount Castle here. And we can also use tiling of these wafers with fiber optic communication to go between a module of tiled wafers, a column of tiled wafers, and more distant regions of the network. How are you going to get data from a wafer to other wafers in a multi-wafer module without using fiber optic communication? The fiber optic exactly mimics the role of white matter in the brain. And then you can repeat this in a fractal manner, just like happens in the brain. So now these are tiled wafers, and now you have more room for bulk fiber optic white matter in between here, and it keeps going on and on. Because you're using light for communication, it's not the size of the neuron that matters. It's the size of the neuron divided by the velocity that communication is occurring at. So if you're signaling at the fastest speed in the universe, that helps you out a lot. So then there's a question, okay, can we reach brain scale systems? I started this project thinking there's no way. I want to prove that the brain is basically insurmountable. And now I'm actually not so sure. Because if you just calculate how big a brain would be with this, meaning something like 100 billion neurons, it fits in a 2 meter by 2 meter by 2 meter cubed. And that's accounting for the white matter connectivity between it, with something on the order of 10,000 synaptic connections per neuron. Okay, so 2 meters is big, but I mean, it would sit right here. You can just put that in your server rack. So power and cooling. Okay, so he's got a question, which I'll answer in just a second. I don't know, this is my last slide because I was going to pitch my poster, but now I already gave my poster, so I'll just leave it at that.
All right, questions, but first I want to ask, when do we get the cube?
I think it's, 6 months to 30 years from now.
It looks like a system you really have to build. I have one question. You need this superconducting current sources to change the weights. How are they built?
Okay, how are the superconducting current biases established in the first place?
These ones you need for your circuit operation.
Okay, so let me just focus here. So this is the synaptic bias current, right? You deliver a current right here to this Josephson junction. This circuit right here, if you see at its output, that is that synaptic bias current. So it's a little bit nuanced, but basically, I picture it, all the synapses on one wafer are going to be fed by one main drive line that's going to mutually inductively couple to this same thing, and then you adjust it on top of that with this circuit right here through spike timing dependent plasticity. So basically what you have is one off-chip voltage source that goes down into the fridge. Then there's a resistor. The resistor is probably also out of the fridge, and that makes it a current source. And then on top of that, you're just fine-tuning through mutual inductors how much actually makes it to the synapse. That's
Sounds great.
it's not that bad.
I really want the power and cooling question.
Okay, so the power and cooling question is, first of all, cooling is manageable with liquid helium. You calculate the total power that's coming out of the wafer here, The wafer is dissipating about a watt if it's going up to something like 100 megahertz and down to 100 hertz, power law distributed across that. So a watt is very easy to remove from this surface area with liquid helium. That's, oh, by the way, I'm assuming that the light sources are 10 to the minus 4 efficiency. We should be able to do better, but I don't want to take anything for granted. So then the total energy, the total power consumption of a brain scale system is on the order of, if it's 10 to the minus 4 efficiency in your light sources, that's something like 20 megawatts, including all the cooling. However, if you can drop off every order of magnitude you gain in efficiency in your light sources, you get an order of magnitude in total power consumption. So it could be as low as something on the order of 20 kilowatts.
So when you say free space communication, that's actually going through liquid helium?
Yes, liquid helium is completely transmissive at infrared wavelengths. And the gentleman has a microphone.
All right, and
Thank
then
you.
last question, then we have to move on.
So, I'm wondering what drove the choice of superconducting electronics, because if you are, decided to work at 4 Kelvin, then the CMOS will be 100 times faster and 10,000 times more energy efficient than at room temperature. It probably would beat superconducting circuits.
It probably wouldn't beat superconducting circuits, but you raise a good point. And I think that is a direction for research that you can come look at my notebook later. Comparing this to how you do it with semiconductors is on my list of things to do. I think that's a valid question. It's not obvious that you can't do similar things with semiconductors. However, I will say, I think superconductors are easier, actually. I mean, these detectors are a wire. It doesn't get easier than that. You don't need any SIGI or anything like that, you know?
All right, thank you again, Jeff.